Hello and welcome. In today's explainer, we're going to go from typing out basic commands all the way to building fully intelligent systems. We're pulling back the curtain on two incredibly powerful tools used by engineers and scientists all over the world, MATLAB and its visual partner Simulink.
But before we get into any definitions, let's start with a big idea. Imagine, what if you had to build something complex, maybe expensive, maybe even a little dangerous, like a chemical reactor? What if you could build it, test it, and perfect it all virtually, right on your laptop, without ever touching a single piece of real hardware? Well, that's the power of simulation, and today we're going to show you exactly how it's done.
So, our journey starts right here, in the world of MATLAB. You can think of this as our home base, right? It's the foundational environment where all the magic really begins. It's basically the language of technical computing, built from the ground up for number crunching, data analysis, and developing algorithms.
So what is MATLAB, really? At its heart, it's a high-level language, kind of like Python, but totally supercharged for math. And that's because everything in MATLAB is designed to work with matrices and arrays. This makes really complex mathematical operations feel incredibly intuitive and fast.
When you open it up, you'll see these four main areas. You've got the command window. That's your direct line to MATLAB. Then there's the workspace, where all your data and variables live. You've got the current folder for managing files, and the command history, which, keeps track of everything you've typed. It's a powerful setup, for sure, but notice something? It's all about text. It's a very code-centric world. So what happens when you need something more visual?
Right. What if your system is constantly changing over time? I'm talking about a dynamic system, like a car's cruise control or the flight path of a drone. For something like that, we need to move from typing code to, drawing diagrams. So let's enter the world of Simulink. And this slide really nails the fundamental difference. Where MATLAB is all about text, driven by commands that you type, Simulink is completely visual. It's all about dragging and dropping blocks that represent different parts of a system and then just connecting them. And look, this isn't just a different interface, it's a totally different way of thinking about complex systems, letting you actually see the flow of information in a way that lines of code never could.
And that, right there, is its superpower. As the source material puts it, Simulink is built for one main purpose: the rapid construction and simulation of these systems. It just takes all that complexity out of the code and puts it into a much more intuitive, visual workflow.
All right, enough theory. The absolute best way to understand Simulink is to just build something. So we're going to put together a simple simulation of that chemical reactor we talked about. We'll start with what's called an open-loop system, which basically just means we give it a command and let it run, with no self-correction. Honestly, the easiest way to think about this is like playing with virtual Legos. Every system needs different pieces, right? And Simulink keeps all those pieces organized in what it calls the library browser. This is our toolbox. Let's open it up.
Okay, every single simulation has to start somewhere. It needs an input signal. To get one, we open up the sources library and we grab a step block. You can think of this like flipping a switch. It creates a sudden change in our input, which is perfect for, say, telling our reactor to go to a new temperature.
Now, we need the reactor itself, the process we actually want to control. This transfer FCN block here represents that. It's basically a compact mathematical model that describes how the reactor responds to inputs based on its real-world physical properties, like heat transfer and reaction rates. It's all the physics of our system packaged up in one neat little block.
So we have an input and we have a system. But how do we see what happens? For that, we need something called a sink. Sinks are just the endpoints of our simulation. We'll grab a to-workspace block, which will save all the output data so we can plot it later and actually see the results of our virtual experiment.
And you can see just how simple it is to put it all together. On one side, we have our three separate blocks, our Legos, the input, the process, and the output. And then we just click and drag to draw lines connecting them. And just like that, we've built a complete simulation of a chemical reactor's core behavior. It's that easy.
Now, our current system is a little basic. We give it a command and it just runs no matter what happens. But what if there's a disturbance? Like, what if the room temperature changes? How can we make the system adapt? Well, we need to add some intelligence. We do that by closing the loop.
So, here's the crucial question. How do we get the system to look at its own output, compare it to where it should be, and then automatically make corrections? How do we make this thing smart? Simple. We give it a brain.
And in the world of control systems, that brain is very often a PID controller. You can find this block right there in the Simulink library. Its entire job is to constantly ask, where are we versus where do we want to be, and then calculate the perfect adjustment to close that gap.
And here's what that actually looks like. In our model, we take the output of our reactor, the real result, and we feed it back to be compared with our original command. The difference between those two, the error, is then fed into our PID controller, which then adjusts the input to the reactor. And with that, we have officially closed the loop.
So, does it work? Oh yeah, absolutely. Just look at this graph. The dashed line is our command. We tell the system to go to a value of 1 right at the 1-minute mark. The system responds, it overshoots a little bit, but then, here's the magic, the PID controller kicks in, corrects it, and brings it right back down to settle perfectly on the target. That is intelligent control in action.
So think about that. We've gone from a completely blank screen to a fully autonomous control system in just a few minutes. So what have we learned, and what can you actually do with this powerful new skill?
Let's just quickly recap the journey. It's a pretty clear 6-step process, right? You start in MATLAB, you open up Simulink, and then you just start building. You grab your blocks, connect them to model your system, add a controller to give it a brain, and then you hit run to see it all come to life.
So, we just modeled a chemical reactor, but you could use this exact same process for a self-driving car steering, a power grid's energy distribution, or a satellite's orbit. The only real question left is, what complex system would you bring to life?